Okay, we've done quite a few questions with two-way tables. Now we're moving on to questions where we should use a tree diagram. Now sometimes a question will help you by telling you to use a tree diagram, but the way to spot whether a tree diagram is going to be helpful is normally when you are given a conditional probability, because then setting up a two-way table may be tricky, but setting up a tree diagram might be easy. So why is this conditional probability? Because we're told about the probability that Josie is or is not waiting at the trough. Okay, so that's straightforward. But the probability that Rosie is waiting at the trough, okay, changes according to when Josie is waiting, and it's different when Josie is not waiting. So we've got these probabilities here. These are conditional probabilities. This one's conditional on Josie being waiting. So on J, this one's conditional on the opposite, on J dashed. So I need to make my events clear. R is the event that Rosie is waiting. And therefore, J I'm going to have as the event that Josie is waiting. Okay, and because I'm doing conditional probabilities, that calls out to be the second stage of a tree diagram. So this is our first tree diagram. This is how they work. Okay, you'll have done them before at GCSE, but let's get the labeling correctly. What we label on the branches, the first branch is going to be for the one that's not conditional. It's going to be for J. Okay, so it's going to lead either to J or to J dashed. Notice that I show the outcomes at the end of the lines. What I put on the lines themselves are the probabilities. So the probability of J happening starting from the beginning, okay, is probability that Josie waits is 0.9 or 0.90. So therefore the probability she's not, well, these cover all the possible cases, so this must be a 0.1. So my first stage of my tree diagram is for whether or not Josie is waiting. The second stage of the tree diagram is going to be about whether or not Rosie is waiting. And I'm going to have different probabilities depending on whether Josie has already been decided as waiting or not, which is ideally suited to this situation because remember I have got these two different probabilities for Rosie and they're conditional probabilities. So the probability I want here is the probability that Rosie is waiting once I already know that Josie is waiting. So that is exactly this 0.7 here. Okay. So therefore, the probability that Rosie isn't waiting, well, again, they add up to 1. So this is 0.3. So the top section of the tree diagram is based on Josie having already been waiting, because that's where the point I've reached. Whereas the bottom section of the tree diagram, Josie is now not already waiting, so I have to use this 0.2 probability here. And so therefore this is a 0.8. So that's why this situation calls for a tree diagram, because the conditional probabilities I've given are exactly what I need for the second stage of my tree. Now, before I read any of the question, what we're expecting to have to do is find the probabilities of all 4 of these endpoints. And to do that, remember what we're doing here is that Josie waits and then Rosie waits. And this is a conditional probability. So you don't have to write this out every time, but I'm doing the probability of J times the probability of R given J. Okay, and as we've seen, when we do a probability and then multiply up by a correct conditional probability, this tells us the probability of J and R. So you're probably familiar with that with a tree diagram. That's a formula for why it works. But all you have to do is just do, for this branch, you do 0.9 times 0.7. So as we work our way through the diagram, we multiply the probabilities on different branches. So here we're going to get 0.63. Here we're going to do 0.9 times 0.3 equals 0.27. 0.1 times 0.2 equals 0.02, and 0.1 times 0.8 equals 0.08. So now I've got 4 different final outcomes, okay? All right, the 4 possibilities are they're both waiting, Josie's waiting and Rosie's not, Josie's not waiting but Rosie is, and that they're neither of them waiting. And these 4 probabilities, if you check, should add up to 1. If they don't, you've done something wrong, because these are all 4 completely separate final outcomes, so they should add up to an overall probability of 1. Okay, so Now you filled this in, we can actually remind ourselves of what the question was about. So part 1 of the question was the probability that they're both waiting at the trough. So I could write both. I could be fancy and I could say that's the probability that Josie's waiting and that Rosie's waiting. But either way, it's this probability here of 0.63. Okay. The second one, the probability that neither of them is waiting at the trough, well, that's this outcome here. Josie's not, Rosie's not, so that's 0.08. And if you've got the tree diagram set up like this with the calculations on the end, then it's okay to write 0.08. And then at least one sow is waiting at the trough. Well, one way to do this is to find out all the ways that this can happen that are good. So sometimes you have to do this. At least one is waiting. Could be both waiting, or Josie waiting but not Rosie, or Josie not waiting but Rosie waiting. So I could add together these probabilities, 0.63 plus 0.27 plus 0.02 equals 0.92. Okay, but what you might see is a quicker way to do this, and it's worth bearing in mind that the probability of at least one of something happening, the only way that that doesn't happen is if it never happens. So if something's not happening at least once, it would have to never happen. So the probability of at least one of something happening is 1 minus the only way that it can't be true that at least one happens, which is that it happens no times, that it's none. So this rule that the probability of at least one of something is always 1, take away the probability of none of those things, this can often take you some time. Save you some time. So in this particular case, you'd do 1 minus the probability that neither of them are waiting, which is 1 minus 0.08, which is a quicker way to get your 0.92. Okay, may have taken a while, but that's because I'm explaining this principle. It's worth maybe making a note of that. Probability of at least one is 1 minus the probability of none. Bet we'll use that again.